So chapter 3, section 2, we're going to learn about logarithmic functions. So here we have the definition of a logarithmic function. We've learned before that if y is equal to log base a of x, if and only if x is equal to a to the power of y. So here we have logarithmic form, and this one is exponential form. And you guys learned in Algebra 2 that you can go from logarithmic form to exponential form and from exponential form to logarithmic form. You can go back and forth. So one trick we can do if we write them on top of each other, if we have y is equal to log base a of x and x is equal to a to the power of y, a stays in the middle, y switches with the x. So that's just one little trick to help you remember. The function f of x is equal to log base a of x is called a logarithmic function with base a. Logarithmic form versus exponential form. These examples just show us that we can go back and forth between the other. If you do the little trick that I showed you on the last one, you have to start with y equals and you have to start with x equals. So this one doesn't start with x equals, so we would just make it start with x equals b raised to the power of y, and then you would just flip the y and the x. So here we have another example. 2 cubed is equal to 8, so therefore log base 2 of 8 is equal to 3. Write each equation in equivalent exponential form. So if we take the b, keep that in the middle, we switch the x to become up front, so x is equal to, and the 4 goes to the back, so x is equal to 2 raised to the power of 4. For example, b, we keep 3 in the middle, make 9 go out front, and make x go up top. So I always think of it as the other side of the equals becomes our exponent. So equals becomes the exponent. So there's different little tricks to help you remember how to go from exponential form to log form and log form to exponential form. Kind of just what you prefer and what helps you remember it. So for this one, we're going from exponential form to logarithmic form. So I like to write the equals first. We have 16 is equal to b to the power of 4. We know our log, base b, is what stays in the middle. Our 4 goes out front, and our 16 goes behind. Same thing with part b. I want to write our x first. So this is a, this is b. I want to write our x first, just so I have x is equal to 5 squared. So I know 5 is what's going to go with the log in the middle. So log base 5. The 2 goes out front, and the x goes at the back. So 2 is equal to log base 5 of the x. For the next two examples here, we have to evaluate the function at the indicated value of x without using a calculator. So we're going to take this x, plug it in for x, and I'm going to call this f of x y, because f of x is just a fancy way of saying y. So y is equal to log base 4 of 64. Putting this into exponential form to solve it, the 4 stays in the middle, 64 goes out front, y goes in the back. So we have 64 is equal to 4y. And we know that we want these to have the same base. So we want 64 to be 4 to the power of something. That'll give us 64. So we know that 4 squared is 16. If we multiply another 4 to that, 16 times 4 would be 64. So this 64 is actually 4 cubed. So 4 cubed is equal to 4 to the power of y. If our bases are the same, we can just cancel them out and set our exponents equal to each other. So 3 is equal to y. For example B, we're going to do the same thing. So we're going to take our x, plug it in for x. So this is y is equal to, well, I guess this is not y, it should actually be f of x. But it doesn't really matter. Our answer here is 3, so that's what's important. So y is equal to log base 36 of 1 over 6. So 36 goes in the middle. 1/6 goes out front. Y goes up top. Now we want either we want to make our 1 over 6 look like a 36, or we want to make our 36 look like a 1 over 6. So we can make our exponent on the left side so that we could change this to 6 to the power of -1, because 6 to the power of -1 would actually make this 1 over 6. So 6 to the power of -1 is the same thing as 1 over 6, so we're just manipulating that a little bit. So we have 6 to the power of -1 is equal to 36y. Now we want our 36 to have the same base as 6. So we know 36 is 6 squared. So this is 6 to the power of -1 is equal to 6 squared times y. Once we have our bases the same, we can cancel them out and just set our exponents equal to each other. So -1 is equal to 2 times y. To solve for y, we're going to divide both sides by 2. So y is equal to -1/2. Now again, this is f of x, but the important part is this -1/2. So we can evaluate logarithms by using your calculator. In the calculator, you just have a log button and we can't change that base. So in the calculator, it's just presumed that that base is 10. So we can put log base 10 of whatever number this is into our calculator. But if we have a different base than 10, we would have to do something else to solve. But it's also important that you practice using your calculator, because some calculators you have to put the number and then put the log button to evaluate. Other calculators you have to click log and then put the number in. So it all depends on what calculator you use, so just make sure you practice using your calculator, like with the homework, so when it comes time for a test, you know how to use your calculator. So use a calculator to evaluate the function at the indicated value of x. So here we have log base 10, which means we can do it in our calculator. We're going to take 2.7 and plug it in for x. So we have -3 times log base 10 of 2.7. So in my calculator, I know I click 2.7 and then log to evaluate. So this is a good one to practice using your calculator to see what you get. So when I do the log of 2.7, I get 0.43136, and then it keeps going. It's best just to keep it in your calculator so you have a more precise answer, because we still need to multiply this times -3. So I get -1.294, and it doesn't say what to round it to, but we can just round it to 3 decimals. So f of x is equal to -1.294. Next, we have some properties of logarithms. So if we take the log of 1, no matter what our base is, anytime we have the log of 1, that's going to be equal to 0, because if we raise any number to the power of 0, our answer is going to be 1. Our second property says if we have log base a of a, that's equal to 1. Because if we put it into exponential form, this should be up here. Anything to the power of 1 is equal to itself. Next property, log base a of a times to the power of x is equal to x. And a to the power of log base a of x is equal to x. So if we rewrote the first one, I always like to have my x out front. So that way I know the a stays in the middle, the x goes up top, and this would be equal to a times x. So that's why this first one works, because a to the power of x is the same as a to the power of x. And then the second one, if we take, again, I like to write equals out front, so like whatever it equals out front. So the a is our log of a. The log of a times x goes out front. The log base a of x goes out front, and then the x goes over here. So it equals to the same thing. So anytime we see that we have the log base a of a times x, it's always going to be equal to that x. And anytime we see a raised to the power of log with that same base, our answer is always going to be this x here. And then our fourth one, if log base a of x is equal to log base a of y, then x is equal to y. So that's the same thing when we have our exponents. When the bases are the same, our exponents are the same. If our logs are the same, then our numbers here are going to be the same. Now we're going to apply our properties. So I have x equals here, 3 goes in the middle, 81 goes out front, and x is our exponent. So 81 is equal to 3 to the power of x. So we need our 81 to look like a 3. We want it to have the base of 3. So we know 3 squared is 9. So that doesn't work. 3 cubed would be 27. That doesn't work. 3 to the 4th power would be 81. So 81 becomes 3 to the 4th power, and that's equal to 3 to the power of x. We can cross out our 3's, so we have 4 is equal to x. The next one, we have log base 5 of 1 is equal to x. If I move my x out here, 5 goes in the middle, 1 goes out front, x goes up top. So 1 is equal to 5 to the power of x. In order to get our 5 to the power of x to look like a 1, we would need our exponent to be 0. So x is equal to 0. All right, for example 6, it says use the properties of logarithms to find the answer. So here we know that if we have an exponent raised to the log with the same base as our number, then our answer is going to be 15. But let's work it out. So here we have x is equal to 3 raised to the power of log base 3 of 15. So this is an exponential. We want to put it into logarithm. So 3 becomes our log with our base of 3. Our whole exponent out here gets moved out front. So this becomes log base 3 of 15. And then our x goes to the back. So if we have log with the same base, log with the same base, we can cancel it out. 15 is equal to x. So this is one of the properties we learned. It is property 3 to be exact. If we wanted to work it out just to test our work to see if we did it right, we definitely could, but we could just look at it and know that our answer was going to be 15 right from the start. So let's look at B. So here we have log base 2 of 2 raised to the power of 3. If we have log base 2 of 2, that same number twice, we know our answer is just going to be 3. But again, let's work it out to test it. So here it's in logarithmic form. This is x is equal to. So we take our base, move it to the middle. We take what's on the right, move it to the left. So 2 to the power of 3 is equal to 2 to the power of x. 2's cancel out, 3 is equal to x. So again, we could see just by looking at it, our answer is 3, but if we wanted to work it out, we definitely could. Here, we have log base 9 of 9. we know our answer is going to be 1 because we have the same base and the same number here. If we wanted to work it out, we could say x is equal to log base 9 of 9. So 9 would be our middle number. We take the 9 on the right, put it on the left, take the x, bring it to the right. So here this is 9 to the power of 1. So if our bases are the same, we know 1 is equal to x. And then for the last one, we can say this is in log form, bring the 3 down to the middle, bring the right side to the left side, bring the left side to the right. And now we want our 3 to look like 1/3. We need to make this a negative x because 1/3 is equal to 1/3 times to the power of negative x in order to get that 3 to be a fraction. Or if we wanted to, we could make this 3 to the power of -1 to get it not to be a fraction anymore. But here we know that this is to the power of 1, and we can set that equal to negative x. So I'm just divide both sides by -1. So x is equal to -1. Next, we have graphs of logarithmic functions. So a graph of a logarithmic function is actually the inverse graph of our exponential function. So the inverse, we just switch the x's and y's. So if you notice this box down here, all of our x terms become all of our y terms. All of our y terms become our x terms. So that's just the inverse. So characteristics of the graphs of logarithmic functions of the form log base b of x. The x-intercept is going to be 1 and there is no y-intercept. So anytime it's in this basic form, our x-intercept is 1 and there is no y-intercept. So it's the inverse of what we were doing before. So before our y-intercept was 1, we had no x-intercept. Now our x-intercept is 1 and we have no y-intercept. So the y-axis, or x is equal to 0, is a vertical asymptote. So this y-axis here is our vertical asymptote. We're going to get really, really close to our y-axis, but we're never going to touch. As x approaches 0 on the positive side, our log base b of x is either going to approach -infinity or infinity. So looking at the first one, we're approaching from the positive direction, so we're going this way. We see that our graph is going down to -infinity. So here, our graph goes to -infinity, and this other one, as we approach on the positive direction, our graph goes up to infinity. So that's what this says, that we approach either -infinity or infinity. And if b is greater than 1, the function is increasing. If b is a fraction that's less than 1, then the function is decreasing. So greater than 1 is increasing. A fraction that's less than 1 is decreasing. The graph is smooth and continuous and has no sharp corners. The domain of the logarithmic function has all the following characteristics. So the log function reverses the domain and range of the exponential function. The range is equal to all real numbers from -infinity to infinity. So before, our domain used to be all real numbers, but now it's our range that is all real numbers. The domain is all the positive real numbers from 0 to infinity and shifts with the horizontal shift. We can find the vertical asymptote by setting the parentheses equal to 0. And this means that if we have log base b of x, we set this x equal to 0 to find our vertical asymptote. And then we can find the x-intercept by plugging in 0 for y. So same thing that we've been doing before. Again, we have transformations of log functions. So if we add something behind our log, we have a vertical translation. These are the same transformations that happen with any function really, but it's the same as when we had our exponential function from 3.1. If we add or subtract something inside of the x, so inside of our parentheses here, it's a horizontal translation. So it's either going to go left or right, and it's going to be the opposite of what you think. So if it's plus, it goes left, and if it's minus, it goes right. If we multiply by a negative, we have a reflection. If it's inside the parentheses, it's on the y-axis. If it's outside, it's on the x-axis. I like to think of it as you want to keep your x's outside your house. So that's why if it's outside, it's a reflection on the x-axis. And then if you multiply by some number on the outside, we have a vertical stretch or shrink. If you multiply some number on the inside of the parentheses, it's a horizontal stretch or shrink. So example 7, graph the function f of x is equal to 3 to the power of x and g of x is equal to log base 3 of x. So to graph, we want to plug in numbers. First we can plug in 1. So when we have 3 to the power of 1, that is 3. So when our x is 1, our y is 3. So you go to the right one, up 3. Put a point there. Next we can plug in 0. So 3 to the power of 0 is just 1. So we'd have our point there. And then next we can plug in -1, which would give us 1/3. So it would be a point right there-ish. And then if we wanted to, we could plug in 2. And we would know that this is 3 squared, which is 9. It would be off the charts up here. So our function is going to have this shape graph. So when graphing the log base 3 of x, it's a lot harder for us to plug in numbers here, but we do know that this function is the inverse of this one. So we can take our x's and y's and just flip them to give us our g of x graph. So these now become our x's. So what were once our y's are now our x's, and our x's are now our y's. So when x is 9, y is 2, so we go to the right 9, up 2. When x is 3, y is 1, I'm going to go to the right 3, and up 1. When x is 1, y is 0. And when x is 1/3, so I go to the right 1/3, I'm going to go down to -1. And then I can connect all of my points with my curve. Got to be careful that my curve does not touch the y-axis, because that's my asymptote. So it's going to get really, really close. It's going to, as it gets closer, as the numbers get smaller down here, your line's going to get closer to the y-axis. So it's going to get really, really close, but doesn't touch. I drew my graph with my finger because my Apple Pencil died, so my graph is not super accurate because it kind of gets further away here. But your graph is supposed to get closer as you go further down here. Alright, this is going to be the last example that we do for the day. So it says use transformations to graph g of x is equal to negative log base 3 of x minus 1. So we have to take one transformation at a time. We know this negative, since it's outside, we keep our x's outside, so it's going to be a reflection on the x-axis, and then a -1 inside the parentheses is always horizontally, and -1 would be a horizontal shift right. So we're going to shift our graph to the right one. So we take our same graph that we had in that last example, where we had log base 3. So if we go to the right 9, we go up 2. If we go to the right 3, we go up 1. If we go to the right 1, we stay at 0, and then we go to the right 1/3, go down to -1. So this was our graph before, and now we have 2 transformations happening to it. So first, we have a reflection, and it's a reflection on the x-axis. So, oopsies. So this is the axis that we're reflecting it on. So we are flipping our graph along the x-axis. So this point up here now becomes down here. This point here is now down here. This point stays the same, and then this one goes here. The 1/3 goes up to 1. So now our graph looks like this. So it's the same thing, but just flipped upside down. We reflected it on the x-axis. So that took care of this transformation here, our reflection on the x-axis. Now we need to shift it right 1. So we are going to take all of our points and just move them to the right 1. So this one at 1/3 becomes 1 1/3. Our point at 1 comes to 2. Our point at 3 goes to 4. And our point at 9 goes to 10. So once we shift all of our points to the right 1, we can draw our line through those points. So this is our g of x graph. So we just had to take our graph from our last slide and apply our 2 transformations to it. So now we can do all of that fun stuff where we have our domain, our range, our x-intercept, and our y-intercept. So our domain, if we're looking at it from left to right, our domain, our graph starts at this asymptote here. So our graph shifted to the right, so our asymptote went from x is equal to 0 to now x is equal to 1. So let's say our vertical asymptote 2, we just said was x is equal to 1. So our domain starts at 1, it never touches 1, so we put a parentheses, and it goes to infinity. So we're going forever in the positive direction to the right, so our domain goes to infinity. Our range is always going to be all real numbers for these. Our x-intercept, where we cross the x-axis, is at 2, 0. It's this point here. And then our y-intercept is none. We never touch the y-axis. So we're going to stop here for today. The notes are due by Wednesday morning, so instead of making them due at the end of class, I decided to give you guys a little bit extra time to get them done, but just make sure you turn in everything that we did. So up to slide 17 is due Wednesday morning, and we'll do the rest of them Wednesday in class.